Welcome to working some chemistry problems. We're going to do a quick work on some of the concepts in Chapter 7, and we'll do a few of the checkpoint problems. And then I'm going to skip over to Chapter 8, and I'm going to focus on drawing Lewis structures. And also that will include assigning formal charges. So we'll do those two concepts. Like I said, the drawing Lewis structures will be some problems in Chapter 8. So looking at Chapter 7, we've been talking about electron configuration, and this kind of brings home some of the properties of the periodic table. So when you look at your periodic table, they're grouped based on their electron configurations. And what this means is they'll have similar physical and chemical properties within a group. Okay, so that's one thing to know. So you look at strontium, which is right after calcium. It's right under calcium in the same group on the periodic table. It's not uncommon that to incorporate in developing teeth of animals strontium. Strontium can actually be incorporated into human teeth, and that's a result from radioactive pollution in areas of nuclear testing, which is very scary, but true because of those chemical properties and physical properties of the same group. Now, a Russian chemist named Dmitry Mendeleev is given credit for developing the periodic table. He developed it in 1869, and the reoccurrence of the properties in a regular repeating fashion pattern is why it's called the periodicity. So this is why it's called the periodic table. By 1900, more than 30 more elements had been added to the list. He had lots of different empty spaces. If you ever can Google online and see the first original periodic table, it's really fascinating. And then Moseley in 1913 discovered a correlation between the atomic number. The atomic number is your number of protons in an element. And so then the periodic table was based on the atomic number more so than it was the heaviness, the weight. Okay, so we have main group elements. And this is what I like. I like the main group elements. And these are called also representative. And if you look on your periodic table that you're given, you see these are like Roman numerals. So you have like, that would be, and these are A. So that would be 5, 6, 7A. So I call that the 7th group. And then you've got transition metals. And transition metals are your D block. And these are 1B through 10B. Well, that's not true. 8B. 1B through 8B. And those are your transition metals, and they'll have different charges. And then you have your F block, which is the lanthanide and the actinide series below that. Another thing that's important in this chapter is understanding that the valence electrons are the outermost electrons, and these are the ones that will participate in the chemical bonding between atoms. And we're going to finish up with counting valence electrons and using this to draw Lewis structures, which is a skill that you'll need to know for your exam coming up. Okay, so we also have metals. 2/3 of the periodic table is metals. The nonmetals typically are to the right-hand side of the periodic table. The noble gases are your group 8A, and helium, neon, argon, krypton, and then you have the metalloids as well. Okay, so let's just do checkpoint problem 7.21. Which electron configuration is correct for germanium in its ground state? So if you look at germanium on the periodic table, you see it's in the p block. It's got an atomic number of 32. And if you go to the, so let's just start with 1s2, 2s2, 2p6, 3s2, 3p6. Now we're on the 4s2, 3d10, and then you see that it's 4p2. And so that is answer B. Now you can go to the noble gas right before, and you can make all of this argon. And then you would just do 4s2, 3d10, and 4p2. But that wasn't an option. Don't worry about 7.22. Okay, the next concept, which is important, is effective nuclear charge. And there's even a formula here that is Z minus sigma. And the reason why this is important, you're not going to actually have to calculate it, but it explains the periodic trends. And I need you to know the periodic trends. And so that's what we're going to be talking about in the next section of this chapter. And these periodic trends can be largely explained by this effective nuclear charge. So what is the effective nuclear charge? It is the amount, so the book says magnitude, of positive charge that the electron experiences. It is experienced by an electron. Now, remember, we care about those valence electrons, those outer electron, the outer electrons in the outer electron shell. And they're easy to pull apart, right? They're going to be easier to pull apart or to participate in bonding if they're further away from the nucleus. And the nucleus has the positive charge. So the electrons that are inside this, the closer to the nucleus, are called the core electrons. So here, all these electrons here in argon, those are core electrons. And they actually shield these outer electrons from the positive nucleus. Now what's happening when you go across a period? So when you go across a period, a row, each element is getting one positive proton added to its nucleus. And it's getting one electron added to its nucleus, or not to its nucleus, but to its outer shell. So it's being added to your subshell. Now keep in mind that if you add an electron to the 2p subshell, well, it's not further away from the nucleus. So here the nucleus gets an extra positive charge, and sure, you added an extra electron, but it's not as effective. So when you add a proton, you get a full positive going across the period, but when you add an electron, it's not going to be a full positive. So this creates some of the trends and the consequences of the trends we see. So let's talk about atomic radius. So let's talk about the trends you need to know. And you can read all of these, but we'll just kind of recap them. You need to know the definition and then the trend. So atomic radius is the distance between the nucleus of an atom and its valence shell, so the outer shell. So if you have something here, they basically say it's this right here. Okay, so in metals, it's defined as half the distance between adjacent metal atoms. Okay, so what's the trend? The trend is for increasing atomic radius. It increases going across a row and down a group. So here, cesium has a very large atomic radius, and you can look at lithium, has a smaller one, but neon, this is neon, has an even smaller one. So neon, same row, lithium, and then you have cesium in the same group as lithium. So if you think about this, as you go down a group, so when you go down a row and you have 1, 2, 3, 4, 5, 6, you know you're getting further, those electrons are getting further away from the nucleus, and those subshells get larger. But because of the effective nuclear charge, the lithium is going to be larger than neon, because neon has 8 more protons than lithium. Okay, so if it has 8 more protons, these protons will attract the outer shell electrons closer to it, so they tighten it up. So it's the effective charge is what the electron, the outer shell electron, experiences, that positive charge. Okay, and then there's ionization energy. Now, ionization energy is written like sometimes IE, and remember, you need to know the name of the trend. So this is a second trend. And you need to know the definition. So ionization energy is the minimum amount of energy required to remove an electron from an atom in the gas phase. So this is studied and it's measured in the gas phase. You can see if you take sodium and then you make its ion and you dislodge an electron, and then that is measured, and that is actually 495.6 or 0.8 kilojoules per mole. And so the first ionization, so you'll see some like IE1 and IE2. The first ionization is that first outer electron. IE2 would be the second removal of the loosely held electron. Now, in general, effective nuclear charge increases, ionization will also increase. So if effective nuclear charge increases, so will ionization. So it increases when you go from left to right across a period. So ionization increases, increasing ionization energy when you go left to right across a period. Okay. Now there are some uneven. So if you look at some graphs on ionization energy, you don't see just your perfect trend. You might see something that looks like this, you know, kind of more like the stock market these days. And that's because when you remove a paired electron, it's going to require more energy. Ionization of an atom in group 6A involves the removal of a paired electron. So like if you look at elements in 6A, so you're looking at like oxygen. If you draw its orbital diagram, you would see it has a paired electron. And the repulsive force between these two electrons in the same orbital actually makes it easier to remove them. So it's actually that ionization energy would be less. Okay, so you can follow those. That's ionization. Let's talk about electron affinity. So now we have electron affinity. Electron affinity is often just EA, and it is the energy released. So it's the negative enthalpy change when an atom in the gas phase accepts an electron. So this is the opposite. So if it accepts an electron, then, so you look at chlorine gas, and if it gains an electron and becomes an anion, this releases 349.0 kilojoules per mole. So this is an exothermic process, and likewise, ionization energy, electron affinity increase going. So increasing electron affinity increases when you go across a period, when you go left to right. And this is due to the increase of the effective nuclear charge that is experienced. And so you can look at those. Let's look at some of your checkpoint problems. Actually, I'm going to just say I'm not going to worry about those because I'm not going to ask you those questions on the exam. Let's go straight to electron configuration of ions. Okay, so a word here is isoelectronic. So isoelectronic, what does it mean? It means that species with identical, the same, electron configurations. So you do have to know this for your exam. And so when we form ions, so you've been doing electron configurations with the ground state element. But what about when you form an ion, then you have to remove maybe one electron. If it's a +1, you might have to remove 2 electrons. If it's a +2, if it is a -1, then you have to add 1 electron. If it's a -2, you have to add 2 electrons, and you do so in its energy. So we're going to write, you'll want to write the electron configurations. Okay, so now we're at 7.52. Which of the following pairs are isoelectronic with each other? Okay, so if you look at calcium 2+, you could see that that is argon. And then you look at strontium, and strontium 2+ would be krypton. Okay, so those are not the same, so that's not isoelectronic. O2- and magnesium 2+. Well, if you add 2 spaces on the periodic table from oxygen, you get neon. And then if you go to magnesium and you go back 2, you go to neon. So those are isoelectronic. So B is a correct answer. Okay, if you go to iodide, you see if you go 1 space because it's negative is xenon. And then that's krypton, right? I mean, krypton is not xenon, so that's not isoelectronic. You look at sulfur, 2-, so you find sulfur on the periodic table. 2- means you move up 2 spots, and you see that's argon. And then you look at Cl-, and Cl- you only have to move up 1 spot, and that's argon. So these are isoelectronic. So we will say D is an answer, so B and D. Helium and hydrogen, that is not, because hydrogen +1 is, I mean, there's nothing, right? There's no electron there. Okay, let's look at 7.5.3. Select the ground state electron configuration for titanium 2+. All right, so let's get this right, folks. Titanium is number 22, and we have, let's see, yeah, so we can go with argon is our first noble gas before titanium, Argon is number 18. And then we come down to 4s2, and then we have 3d2 as our ground state. And your book does this 3d2, 4s2 for its ground state, which means then when you take the 2 electrons away, you take them from here. And so argon 3d2 is the answer, and that's D. Okay, 7.5.4, select the ground state electron configuration for the sulfide. So let's look at sulfur. The first noble gas before that is neon, and then we come down to 3s2, and then 3p4 for its ground state, but we're adding 2 electrons. So we're going to add 2 electrons to make this 3p6, which is also argon. But let's see what our options are. And it looks like we have to go with neon, 3s2, 3p6, which is answer is B. And that's doing ions. Okay, now we're going to talk about ionic radius. So these are more trends. 7.6.1. Which of the following species are isoelectronic? There's our word again, same electron configuration with krypton. And so you can just find krypton and you see that Br minus would be one of them. Argon, of course, can't. Neon and helium can't. I mean, those are noble gases. And then also rubidium Rb plus, because if you find rubidium, it's a group 1, and you move backwards 1 electron, then it's going to be isoelectronic with krypton, so that is also E. And then let's do 7.6.2. Which of the following are arranged correctly in the order of increasing radii? So when you look down the group 7, so if you look down group 7A, you see you've got iodide, you got bromide, you got chloride, and you got fluoride. And iodide is going to just be huge, and they're just gonna, this is the trend. Okay, so they get bigger as you go down. So A is the answer there. You can read about the chemical properties, and I think that that sums up what I think is important in chapter 7. I told you that I want to skip over to drawing Lewis structures. So let's go to section 8.5. So we're in section 8.5, and we're going to do 8.5 and 8.6 in this little session here, because I want you to get used to practicing drawing Lewis structures. It takes a little bit of time, and you all have a week, so I want you to start doing the Lewis structures. So you're going to be given molecular formulas, and step 1, you're going to have to connect them. So you're going to draw lines to connect the atoms. So we're basically going to draw single bonds to connect atoms. And these are bonds. We're going to talk about how those are covalent bonds. So connectivity is step number 1. So the first thing you got to do is you got to join every one of these elements. Now the least electronegative atom will be the central. And I might help you out with identifying the central atom on some of these, but the least electronegative atom. So let's just show that trend. That's my most important trend. So increasing electronegativity, and we'll talk about that. That is the ability for the element to attract electrons towards itself. And so the increase in electronegativity increases going up a group and it increases going across the row. So to know some true numbers, fluorine is the highest electronegative element, and it's a 4.0. That's what we all want in school. The least electronegative element is going to be francium, and I think that's like a 0.96, so it's not even 1. And Linus Pauling got a Nobel Prize for assigning electronegativities and charts and bonding. These bonding concepts are what we follow. So the least electronegative atom between the two would be their central atom. Okay, and then so connectivity, we're going to have to connect the bonds, connect the atoms. Step 2. Step 2, I want you to count your total valence electrons. I call these VE, valence electrons. And the valence electrons is the group number of that atom. So if you have like hydrogen and carbon and nitrogen, hydrogen is group 1, so it has 1 valence electron. Carbon is group 4, so it has 4 valence electron. And nitrogen is group 5, so it has 5 valence electrons. And you add these together, and you get 10 valence electrons. So that's how we count our total valence electrons. And of course here, if they're in a line like that, you would connect them like that, because that's step 1. Connect them. And the carbon is to the left of nitrogen, so it would be in the middle. You'll learn hydrogen is never central. Hydrogen can only do 1 bond. It has, because it's special. It's just up there. It can only have 2 electrons. So hydrogen will never be in the center. Will always be a terminal. Fluorine will always be. So you could always, these are the things you got to memorize. Hydrogen and fluorine always single bonds, and they're always terminal. So they'll never be in the central atom. Okay, 3, for each bond, dash and subtract 2 electrons. I don't do that. Use the remaining electrons to complete the octets of the terminal atoms, placing pairs of electrons on the atom. That's okay. If the electrons remain, place them in bonds on the central. Okay, so basically, let's do what it's trying to tell you. Step 3, we're going to add valence electrons to the atoms, and we're going to go outer to inner. Okay, so we're going to go outer to inner, but you need to follow the octet. So you want to complete the octet. So step 4 is going to be the octet. So those are going to be 4 steps we follow. Step 4 is the octet rule. And the octet rules means, you think of an octagon, right? So it should have 8 electrons. Now we do have expanded octet, but for most part, most things are going to follow the octet rule. There are exceptions, and we'll have to talk about those. You'll see group 3A is an exception, hydrogen is an exception, and helium is an exception. So because they only get 2 electrons in their bonding. 3A they can have 8, but they typically have 6 electrons in their bonding. All right, so let's work CS2 and try these 4 rules. Okay, so we have CS2. That's carbon. You should know how to name these. 2 nonmetals, carbon disulfide. Now, which is, if you increase electronegativity up and over, carbon will be your central atom, and then sulfur's on the other side. Okay, so we did our connectivity. Now the second thing, you have to count total valence electrons. So step 1, we did our connectivity. Step 2, total valence electrons. Remember I told you the group number? So carbon's group 4, sulfur is group 6. There are 2 of them, so that's 12. 12 plus 4 is 16. Now, if this had a negative charge, you'd have to add electrons. If it had a positive charge, you would subtract them. Okay, so we have that step 2. We've counted our valence electrons. Step 3, we add electrons on the outer elements, and then we work inward. And so how many do we add? We follow the octet rule. So you've got to already count these 2, so that's already 2 for sulfur. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So what's 8 plus 8? 16. Okay? So that's 16. We can't add electrons or take them away. We have to follow this. Total valence electrons are 16. But now we have to do the octet. Step 4 is the octet. And that means every element wants 8 electrons, because that would be a complete shell. That would get it to one of those noble gases, a complete outer shell. So sulfur's fine. The problem, so this is fine. 1, 2, 1, 2, 3, 4, 5, 6, and these are counted as 2. So we have 8. You can put a smiley face. Sulfur's happy. This sulfur's happy. 1, 2, 3, 4. A bond counts as 2, so it's happy. Now, carbon only has 1, 2, 3, 4. Carbon has 4 electrons, and it needs 8, and it's very unhappy. So what you need to do is we're going to have to, we can't add more electrons. We can only work with 16. So you need to convert these, what these are called is lone pairs. Lone pairs on the sulfur into multiple bonds. Okay, so that means that these 2 electrons can go here, and we'll form, and then we redraw. So you do that, and then you still have these 2, and then you have sulfur here. Now you know this sulfur's still happy. This one's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. That one's happy. And what about carbon? Carbon has 1, 2, 3, 4, 5, 6. It's still unhappy. Okay, it needs octet of 8. So now we can do the same thing here. And we'll make that a double bond. So then, and we redraw. We got to redraw. 1, 2, 3, 4, 1, 2, 3, 4, and then we check our octet. Sulfur, 1, 2, 3, 4, 5, 6, 7, 8. This sulfur has 1, 2, 3, 4, 5, 6, 7, 8, and this carbon has 1, 2, 3, 4, 5, 6, 7, 8. They all follow the octet rule, and so this would be a correct Lewis structure for carbon disulfide. Okay, let's try the NF3. So we have another one, NF3. Now we know fluorine's our most electronegative atom, so we're going to put nitrogen in the middle. I told you fluorine and hydrogen are always terminal, okay? Now, so we did our connectivity, step 1, connectivity. And then step 2, we need to add our total valence electrons. So nitrogen is group 5, group number 5. And fluorine is group number 7. And there's 3 of them, so that's 21. So what's 21 plus 5? 26 total valence electrons. And now we add them, and we go from the outer. So step 3, we go outer, we add electrons, outer, and work our way inward. And we have to make sure they get the octet rule. Okay, so fluorine has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So after you get complete octets on the outer, then you put your extra on the inward. And then you make sure the nitrogen follows the octet. So nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. They all have 8 electrons, so they follow the octet rule. And we have 26 valence electrons. So this is a correct Lewis structure. All right, so let's do checkpoint 8.51. Formic acid, HCOOH. All right, now this is a little bit more challenging for the connectivity. So hydrogen, I told you, is always terminal, and this carbon is connected to oxygen, but it's also connected to this oxygen. So I would feel like I need to give that to you, that connectivity, and then you do your total valence electrons. So carbon is 4, hydrogen is 1, there's 2 of them, so that's 2. Oxygen is 6, and there's 2 of those, so that's 12. So 4, 5, 6, 7, 8, so we have 18 total valence electrons. Hydrogen can't have any more, it only has 2, 1, 2, 3, 4, and so then oxygen 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. All right, so now we look, hydrogen is okay because it only needs 2 electrons for its octet rule. Oxygen here, 1, 2, 3, 4, 5, 6. That one's fine, 1, 2, 3, 4, 5, 6, 7, 8. That one's fine. But carbon is unhappy because carbon only has 1, 2, 3, 4, 5, 6. So we're going to take the oxygen that has these extra, and we're going to, those lone pairs, and we're going to reposition them on carbon and make a double bond there. We'll keep those 2 electrons. And then we're going to recount. And 1, 2, 3, 4, 5, 6. And then do the same thing with carbon. 1, 2, 3, 4, 5, 6, 7, 8. So they all have complete octets. And if you look, that is solution D. And hydrogen peroxide, H2O2. The oxygens are connected to each other. The hydrogens have to be terminal. You add your total electron count. There's 2 oxygens. Group number 6 times 2 is 12. 2 hydrogens plus 2, that's 14. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And you'll see that they all have a complete octet because hydrogen only needs 2. And you'll find that hydrogen peroxide works because that's a very weak oxygen-oxygen bond. Now, you will need to also assign formal charges. And so let me tell you how to do formal charges. So formal charge is a lot of times when you see a polyatomic anion, like SO4 2-. Okay, so let's look at something like that. So sulfur is, and I will just show you this. This is its Lewis structure. Okay, so that is the sulfate anion. Okay, the polyatomic anion that you all have memorized with the charge. Now, to do formal charge, you need this formula. Group number minus dashes minus dots. And that's also formal charge is group number. GN is group number. Dashes is covalent bond. So however many covalent bonds. And the dots are lone pair electrons. So if you look at sulfur, sulfur has a group number of 6. It's group 6. It has how many dashes? 1, 2, 3, 4. So it has 4 covalent bonds, and it has 0 lone pairs. Is that right? And did I, oh, SO4. Sorry about that, folks. Here, let me write, let's put the other on there. Okay, and sulfur has an expanded octet, so let's do this again. 6 minus what? 1, 2, 1, 2, 3, 4, 5, 6. So that's 0. So sulfur doesn't have a charge, a formal charge. Oxygen, oxygen. Let's look at this oxygen, and let's look at this oxygen. Okay, so let's look at the oxygen, and both of these will be the same. The group number is 6 minus 1, 2, 2 dashes, minus 1, 2, 3, 4, minus 4 dots. So 6 minus 2 is 4, minus 4 is 0. So these oxygens do not have a formal charge. Now let's look at these oxygens that I put the negative on there. And this is how I knew to put the negative on there. Those oxygens have a group number of 6. There's 1 bond, so minus 1, minus how many dots? 1, 2, 3, 4, 5, 6, minus 6. So 6 minus 1 is 5, minus 6 is a negative 1. So each one of these has a negative 1 formal charge. And so this actual structure tells you that the negative charge is on the most electronegative element, which is oxygen. So this tells you charge. Let's look at an example of ozone. So ozone is being depleted in our environment. And the guy that actually got the Nobel Prize for that actually died, I think, this past month. But anyway, so oxygen, ozone is like this. This is the connectivity. Let's do its Lewis structure. Let's count up total valence electrons. So oxygen is group number 6, and there's 3 of them. So that's 18 electrons. There's no charge. Now we work outward to inward, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And so oxygen's fine with the octet. So now we're going to check our octet. That outer oxygen's fine. This one's fine. This one is not fine. It only has 1, 2, 3, 4, 5, 6 electrons. So now we're going to take one of these and we're going to share it. And then we're going to redraw. And oh, okay. So now we have 1, 2, 3, 4, 5, 6, 7, 8. We have 1, 2, 3, 4, 5, 6, 7, 8. And we have 1, 2, 3, 4, 5, 6, 7, 8. So they all follow the octet. Now, what about their formal charges? Well, this oxygen, the red oxygen, has a group number 6 minus, so formal charge, group number minus dash minus dot. It has, so 6 is its group number. It has 2 dashes, and it has 4 dots. So 6 minus, that's 0. Now this oxygen, the middle oxygen, is 6 minus 1, 2, 3. And how many dots? 1, 2. So 6 minus 3 is 3. Minus 2 is a plus 1. So this oxygen is a plus. And you don't have to put the 1. And then we have this oxygen over here. And that formal charge is 6 minus 1 minus 1, 2, 3, 4, 5, 6. So 6 minus 1 is 5. Minus 6 is a negative 1. So there's the negative. So you see how this is the Lewis structure of ozone. And even though, see, it's a neutral compound, it still has a plus minus on the different oxygens. I can recognize these very quickly because I know my common bonding patterns. And if you're planning on going to organic chemistry, that's the thing I teach students the first day. And so I'm going to tell you the common bonding patterns of the elements that you see in organic chemistry. So hydrogen, I'll say loves one bond, one covalent bond, and 0 lone pairs. Okay. Um, and then we can go on to boron. Boron loves 3 covalent bonds and 0 lone pairs. You go to carbon, which is next to boron, and carbon loves 4 covalent bonds and 0 lone pair. Nitrogen, nitrogen loves 3 covalent bonds and 1 lone pair. Oxygen, oxygen loves 2 covalent bonds and 2 lone pair. And then you get into fluorine. Fluorine loves 1 covalent bond and 3 lone pairs. So maybe you can see the trend in your periodic table. You get into lone pairs with nitrogen, oxygen, and fluorine, and they start decreasing the covalent bonds. So you go 4, 3, 2, 1. So you go 1, 3, 4, 3, 2, 1. And the reason why the common bonding patterns is good is because you look at oxygen here. Oxygen, this red oxygen, it has 2 covalent bonds and 2 lone pairs. I know I don't have to do formal charge. I know it's going to be 0. I look at the middle oxygen and I see that that oxygen doesn't have 2 covalent bonds. It has 3. It has 1 lone pair. So it does not follow the common bonding pattern. So I know I'm going to have to do this formal charge. This oxygen here, it has 1 covalent bond and 3 lone pairs. So I know it's not following the common bonding pattern, so I'm going to have to assign a formal charge. And it makes it nice because then you don't have to assign a formal charge for every element. Let's do your checkpoint. So determine 8.6.1, determine the formal charges on H, C, and N for hydrogen cyanide. So let's do the Lewis structure first. There's my connectivity. Hydrogen has to be at the end. Carbon is more electropositive than nitrogen. Total valence electrons. Well, hydrogen's group 1. Carbon is group 4. Nitrogen is group 5. So this is 10 valence electrons. We work our way outward, and then we go in, and we follow the octet rule. So hydrogen doesn't get any. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We check our octet. 2 makes hydrogen happy. Nitrogen's happy. Carbon is very unhappy. It only has 4 electrons. So now we're going to put those electrons in and we're going to redraw. So hydrogen, carbon, double bond nitrogen. Keep those other 2 electrons, and we count. Hydrogen's happy. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. It's happy. Carbon has 1, 2, 3, 4, 5, 6. It's still unhappy. So now we're going to take another lone pair and throw it in there and redraw. HC, triple bond nitrogen. And now we're going to check it. Hydrogen's good. Nitrogen has 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 4. So there is your Lewis structure. Now I know my common bonding pattern. So I know hydrogen loves 1 covalent bond and 0 lone pairs. So it's fine. Carbon loves 4 covalent bonds and 0 lone pairs. I can see it's fine. Nitrogen loves 3 covalent bonds and 1 lone pair. I can see it has exactly that. But now you might not know your common bonding pattern, so you have to do the formal charge where you go group number for hydrogen is 1 minus dashes 1 minus dots is 0. So 1 minus 1 is 0. So formal charge on hydrogen is 0. Carbon, group number 4 minus 1, 2, 3, 4 dashes, 0 lone pairs, 0. Nitrogen, group number 5 minus 1, 2, 3, 3 dashes, minus 2 dots, 5 minus 3 is 2. Minus 2 is 0. So your answer for that is E. Okay, let's do 8.6.2. Which of the Lewis structures shown most likely preferred for NCO minus? Okay, so carbon, that's my connectivity, and we're going to do the total valence electrons. So nitrogen's 5, carbon is 4, oxygen's 6, and then we have a plus 1 because of the negative charge. So we have 16 valence electrons. So now we do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, and let's take this negative away because right now all you know is this thing has a negative charge, but we don't know which, where, what atom does the negative charge reside. And that's what the formal charges tell you. Okay, so here, nitrogen's okay with the octet rule, oxygen's okay, carbon is not. So now we're going to just put those in and redraw. And now, once again, these are okay. Carbon's not. Now I know nitrogen likes 3 bonds and 1 lone pair. Carbon likes 4. And so the negative is going to be on oxygen. And we can just do our check. So nitrogen, group number, formal charge, group number is 5, minus 3 dashes and 2 dots. 5 minus 3 is 2, minus 2 is 0. You can do carbon, formal charge, group number 4 minus 0 is 0. And then oxygen here is group number 6 minus 1 dash minus 1, 2, 3, 4, 5, 6 dots, negative 1. So there it is. Also, so I recognize the oxygen. And what does oxygen love? 2 covalent bonds and 2 lone pairs. And so that's also another way to recognize it. And the negative charge is going to be on the more electronegative atom. So because the negative charge will prefer the most electronegative atom. And it looks like that would be C for your answer. And that wraps up where we're at this point.